second part of the analysis this week, and we shall start with the differentiability. So it's very advantageous to introduce the functions of the class C1. So we shall say that f is in C1 on an interval RAB when f dash not only exists, so the derivative exists and is continuous. So we want both. We want the existing derivative and the continuity of the derivative. And we will see immediately why this is necessary. Actually, we saw it already, because if we know that the inverse function, so f2 minus 1, exists, and f2 minus 1, so the f inverse composed with f is identity, right? So identity on the interval where we work. And we know that the continuous functions, so if we want to deal with those differentiable, then we shall call the C1 once differentiable functions. Well, ck will be k times differentiable. So it means that the k minus first derivative is in C1. That will be ck. And if we know that f is differentiable, and if we expect that f inverse exists and would be also differentiable, then of course we see immediately from the chain, or from the definition, from the chain rule, the rule for differentiating the composition of functions, we see that the derivative of the inverse must be what? Well, so basically what we can see is here, if I put the derivative sign here, so I must do the same here, and this is 1, right? And here I know how to differentiate. So it will be the derivative of the whole thing here is the derivative of the outer function, so it's this one, times the derivative of f, the inner function. This one will be evaluated at fx, and this one is at x. Right? But it means that of course that the derivative of the inverse must be the derivative of the inverse at fx must be 1 over the derivative of f at x, right? And that's it. That's what we've got here as the theorem. So if we have a real valued function differentiable at that point y0 such that the inverse exists on a neighborhood, so we expect that the inverse exists, right? Then we know that it's this way. But if we know that f is in C1, then if the derivative of f is 0, then the inverse function perhaps won't exist. And if it's non-zero, then it must be non-zero on the neighborhood, but then it has got the same sign on the neighborhood. And the effect of the example I told you and explained to you in the previous presentation can't happen, right? So the problem that you have something which seems to be growing at a point, but is wiggling at every neighborhood, so that it's decreasing, increasing in a change, then of course the inverse wouldn't exist. But if it exists, it must be this way. And then the proof is pretty easy, right? So the proof is here on a few lines. So you don't have to take care. And that's the reason why it is that if the derivative is the right one, so it grows, right? And then it's okay. Right, let's have a look. Let's have a look how it is with the elementary functions. We know how to differentiate the polynomials, We know that the inverse on these intervals where the polynomials would have constant positive, or well, no, would be growing or decreasing, and therefore there would be on those intervals the inverses. For those cases, we know that it won't be polynomials again, mostly, right? But we still can compute the derivatives because it's just the reciprocal value. Well, I perhaps also had to draw it on a picture because that makes the life much easier. So you can imagine if you have the function f, say this way, then the inverse function would be just the flip across the diagonal of the first quadrant. So that will be the inverse functions, right? And you see that the slopes are actually the same slopes as, so if you look at the tangent here, so the slope of the tangent, so it's just this ratio of the value. So this is the delta of y and this is the delta of x. And if I just view the same picture the opposite way, just viewing it as the inverse function, then I simply take it del x over del y. So the slope of the inverse function is just the reciprocal value, right? For the power and exponential function, I perhaps didn't tell it last week, so let's go quickly for that now. So this is something which I skipped. So it's actually very easy to define them by using the continuity assumption, right? So the point is that what we know is how it looks like if you go with real x, any real x, and natural y or z, right? So if y and z are natural numbers, then directly from the definition of multiplication and how we take the power functions, so we know that x to y must behave this way, right? So if this is just we multiply x y times, this is we multiply x z times, so that's the rule, and therefore there is a straightforward consequence again for the real x and natural y's and z. Then we can easily move on and say that if we want to add the negative powers, then we simply take the reciprocal values. So that's again okay. Then if we want to go to the rationals, we simply want to solve the equalities. B to n is x, and we did that already because we defined the root function, so the roots, right? So this is the b is the nth root, and we know how to do it. That was done already last week. So that's easy. And now, because the power function is always either increasing or decreasing, and once we restrict ourselves to, well, we had already with the roots to restrict ourselves to the positive or non-negative axis only, so that makes life easier because we know that it will be always either increasing or decreasing, and so we can use the supremum existence, and we define exactly as we did it with the roots. We define the values of the power functions, right? So that's again easy. So that's the definition, right? So we know it for all the rational ones, and that allows us to use the supremum or infimum to get the values. And finally, well, that's the growing one with x between 0 and 1, it will be the other one, but we can also use the inverse, the reciprocal value, and that's okay. And of course we can now swap the roles of x and a and look at it as x is constant and a is the variable, and we get then the exponential function which grows like a rocket here, right? So that's what you see. And the inverse function to that, because it's always either increasing or decreasing, so there is the inverse, and that's called a logarithmic function, right? And here through the construction, the property we started with and we used for the definitions survives the suprema, and therefore just adding the continuity assumption to this property 1 ensures that our power function and exponential functions will exist, they will be the unique ones, and they will obey these properties. So that's very good. And then we know there will be the inverses, right? And the inverses from the same rules, we immediately this is the definition of the inverse, and it must just obey this property. That's very good. So that's what I am coming back to what is in the text before derivatives, and now we can come back to the computing of the derivatives of those. So we are here. So that was the inverse function theorem, and here we can just compute, right? So here what's clear is that if we take the exponential function, then the derivative is easily computed from definition as the derivative at 0 times the same function. So you see the exponential functions are the nice functions or unique functions, therefore they are so useful, where the derivative, as we shall see, always exists and is proportional to the original function, and the constant proportion is given by the derivative at 0. So unfortunately we are not having now the tools to show that the derivative at 0 exists, but we shall come to that in the next week. But let's believe it does, and then there is a unique base which is called the Euler number E, so this one, where the derivative in 0 will not only exist but will be 1. So this is a unique function which grows as fast as it has the value at the moment, right? So that's very good. And of course, once we know that the derivative of the exponential functions would exist, then we can also determine the logarithmic functions, how to differentiate them, because we just know how it is. So you see that just by the very definition, that's the definition, and the computation by means of the theorem we just discussed shows that it will be exactly this nice formula. So the derivative of the logarithm is 1 over the value, so it's the reciprocal value of the argument. And now, because we know also the formula for differentiating general power function, which is easy to derive, you can compute it easily by this, right? So x to a is the same as e to a times logarithm. And now you use the rules for differentiating the composed functions, and what we end up with, that for all power functions the same formula holds true as with polynomials, independent of the a is. So for each real a. This is one of the most important things we shall see also in all the computational powers we shall meet. Right, so that's about the derivative differentiability and the application, how to use this to compute the derivatives of the elementary functions. And I also promised to go quickly through some mean value theorems, which is very straightforward and easy. So there is this Rowlett theorem. Rowlett theorem says that if you have a function which is defined on a interval and is differentiable inside, which means it does have derivative at each point inside. So it's not differentiable. It's not necessary to have it differentiable in the sense of the C1 category, as I was talking about in the beginning. We just need to see the derivative to exist at each point, and we want the function to be continuous in the ends of the interval, in the boundary points. And then if the function values are the same in the boundary points, then there must be some point C in the middle where the derivative is 0, right? And that's very easy to see because we know that if it has got derivative at each point, then it must be continuous at each point. And if it is continuous at each point, it's continuous on the whole interval, including the boundaries, because that's in the assumptions. And then the image of continuous functions on a compact interval, which is compact because it's a finite interval, is again an interval. And there must be a maximum of the function. And if the maximum is in the boundary values, then it means that they are the same ones. So, well, so then either there is some point inside where it also, well, it must have got both maximum and minimum, right? And either both maximum and minimum are in the boundary points, then it's a constant function, or there exists at least one point C where the function has got local minimum and max or maximum, but then there the derivative must be zero, and the derivative exists by the assumption, right? So this is the Lagrange mean theorem, is just the same thing. It just says that if you have a function and you take the values in the 2 points, then the second must have the same slope as the tangent somewhere in the middle, right? And this is the consequence of that. So it's very useful. We shall use the Lagrange theorem many times, and the proof is the typical mathematical approach. Just transpose what your task is to something you have done already. So you simply find another function. You can imagine you simply take another function, just sort of transforming the thing so that it will be having the same value in both boundary points, and that's the way how to do it, right? So you simply add to the function f some linear term, and then you apply the previous theorem. Very easy and straightforward. This is again the same thing. But in terms of a curve. So you will have two functions parameterizing a curve which is differentiable. So you can imagine a complex valued, you can also imagine a complex valued function of one variable on interval a, b, and f and g will be the real and imaginary part of it, right? And then the claim is that the ratio of the differences of the boundary values of the function must be achieved as a ratio of the derivatives inside. And again, the proof is just a very straightforward application of the previous Rollet theorem. Very easy. And the last thing, which is very important and very useful very often, is the L'Hopital's rule. So L'Hopital was an old entrepreneur who wanted to be famous as a mathematician. He loved mathematics, but he wasn't thinking about doing everything himself. So he hired mathematicians who worked for him for money, and he was publishing their results under his name because he was just, of course, owning the results when he paid for them. So that's not how the science is done these days. But the L'Hopital's rule says, again, a very straightforward thing. It's best seen from the picture, right? So you've got here the function, and imagine you take all the seconds, right? And if the function is, if it goes from the beginning, so if it goes from the origin, so the slope of the seconds will be gt over ft, and the slope of the tangents going to 0 will be g dash over f dash, right? And from the picture it's clear that if the function is beautiful enough, it's differentiable enough, then the two things, the two sequences of slopes should have the same limit. And this is actually true, right? So the only question is in which way we can just make it to a implication, because of course it looks like it must exist in both cases and must be equal for beautiful enough curves. And now the mathematics part, so the pure mathematics part, the deductive thinking comes in and asks, well, so what are the real conditions? So what is really a sufficient condition at least, right? And the sufficient condition is if the limit of the derivative exists, then also the limit of the values exists, which can be expected because the limit of the derivatives gives you sort of more detailed guess how the function behaves than the limit of the seconds, right? So this is really true, and the proof is a little bit tricky, so it's not very bad. So you see, I just use the emoticon to explain it as the easy one, and then no other appears, so it should be very easy. And you can also have the same for the improper limits, so you can just have it if the limits are plus minus infinity and or you go to in plus minus infinity, the x0 might be an improper point, and this is what's there. And finally there is an example. So if you are interested in the example, it links the arithmetic mean and the geometric mean, the harmonic mean. Right, so that's perhaps what I it's more than what I had to say, and took more time than I hoped to spend. So let's hope you will go through, and I'm looking forward to meeting you at the chats and answering your questions.